Large tables make offset and limit M unusable. The database must scan N rows before returning the M requested rows. Consider a 10 million row table. Fetching page 1000 means the engine scans 9.99 million rows just to discard them. This is O of N complexity relative to the offset value. This latency spike is unacceptable for high-traffic APIs and guarantees resource exhaustion under load. We require O of 1 or O of log n pagination regardless of the requested depth. Keyset pagination achieves this by eliminating the row count scan entirely, shifting the burden from row counting to index seeking. The database engine executes the order by clause first, establishing the complete result set order. Only then does it discard the first n row specified by offset. This discard operation requires materializing or scanning those rows, even though they are never returned to the client. If the order by column lacks an index, the performance hit is compounded by a full table sort operation. Even with an index, the index scan must traverse n entries sequentially. This inherent inefficiency makes deep pagination a denial of service vector against your database resources, consuming input-output operations and memory unnecessarily. Keyset pagination, also known as cursor-based pagination, avoids the row count mechanism entirely. Instead of specifying how many rows to skip, we specify the exact values where the last page ended. The query uses a where clause based on the values of the last retrieved row, typically involving the primary key and the sort column. This approach leverages existing B-tree indexes directly. The database performs a highly efficient index seek operation, starting precisely at the next required entry, transforming the operation from a linear scan into a logarithmic lookup. Keyset requires two critical prerequisites for correct and efficient operation. First, the sort order must be stable and deterministic. If the sort column, for example, a non-unique timestamp like created at, contains duplicate values, you must append a unique tiebreaker, typically the primary key. Second, a composite index covering the sort column and the tiebreaker column is mandatory. For sorting by created at descending, the index must be defined as a composite index on created at descending and identifier descending. Without this specific composite index, the database cannot perform the necessary range scan efficiently. Assume we are fetching 50 posts sorted by score descending, and the last post seen had a score of 450 and an identifier of 1234. The next page query must use a compound where clause. The query becomes select identifier, score, title from posts where score less than 450 or score equals 450 and identifier less than 1234. Order by score descending, identifier descending, limit 50. Notice the structure. We look for rows with a strictly better score or rows with the same score but a better tiebreaker identifier. This structure ensures the database only seeks the index starting immediately after the last known point, guaranteeing O of log n performance. Complex sorting, such as sorting by status then by updated at, requires extending the keyset tuple to match the full sort criteria. If the last row was status pending and updated at 2024-0101, the where clause must check the status first. The condition becomes where status less than pending or status equals pending and updated at less than 2024-0101 or status equals pending and updated at equals 2024-0101 and identifier less than last identifier. The composite index must match this full sort order exactly, status, updated at, and identifier. Any deviation in the index definition will force a less efficient operation. Keyset pagination fundamentally sacrifices random access capability. Users cannot jump directly to page 50 because the system requires the cursor value from page 49 to construct the where clause. If your application requires displaying total page counts or allowing users to navigate non-sequentially, offset pagination remains the only viable option, despite its known performance cost. However, for modern user interfaces relying on infinite scrolling feeds or standard next previous navigation, Keyset is the superior architectural choice, prioritizing speed over random access. Exposing raw Keyset values like score equals 450 and identifier equals 1234 in the URL is insecure and messy. Always encode the cursor tuple, typically using base 64 encoding, to create an opaque token. This prevents user tampering with the underlying database values, which could lead to unauthorized data access or query manipulation. Furthermore, ensure the cursor includes a timestamp or a hash of the sort criteria. This allows the backend to detect stale or manipulated requests, maintaining data integrity and preventing unexpected behavior when the underlying data schema or sort order changes. Mandate Keyset pagination for all high-volume, deep-scrolling endpoints, especially those expected to exceed 10,000 records. Reserve offset/limit strictly for administrative interfaces or low-volume queries, where the maximum offset is capped, perhaps at 1,000 rows. Implementing Keyset requires upfront schema planning for the necessary composite indexes, but the resulting performance gain is non-negotiable for scalable application architecture.
Moving from linear time complexity to logarithmic time complexity ensures your application remains responsive even as data volume increases exponentially.